So I just checked out the font. Is the font big enough for the back? Okay, you can see the font. Okay, so I just checked out a fresh copy of the Python 2.7.8 code base. So this is the latest one online, 2.7.8. Showing there's no magic here. I'm just gonna untar it. Just a bunch of source files, C and H files. So the Python interpreter is all in C. And the goal today is to go over both the bytecodes themselves and how they're executing the interpreter. And then I'm gonna release the first assignment tonight. So the first assignment's actually due this Friday afternoon, 6 p.m. So, but after today's lecture, you should be able to do the assignment. So like, you have basically a week. Wow, it takes a while to unzip everything. Okay, so we can cd into here, and there's a bunch of files. So you can zip it on whatever computer you have. I'm going to use Sublime Text to view it. So what actually I did was, here, let me start from scratch so you can see. You can use whatever editor you want. So all I did is I actually opened a folder. So I actually went to my, oh no. I actually went to my home folder, Python 2.7.8, and opened it. Let's go here. I just opened the folder, and that has all the files in it. So today we're going to focus on two files in particular. So you can pull them open if you want. You can use whatever editor you want. It's an include, so it's /include called opcode.h, opcode.h, which is not that one. This one, opcode.h and include. So you can pull that up. I have this in the course schedule also. So pull that up in whatever editor you want. And the second file we're going to pull up is, I'll make the font bigger, so don't worry. The second file we want to pull up is in Python. That just overwrote it. I'm going to use my mouse. Include opcode.h. Okay, and the second file we're going to open is in Python itself, and it's called ceval.c. So you have ceval.c and opcode.h. Those are the two files. So wait for a second while everyone opens those files up in your favorite editor. And I have line numbers on the left here, so you can jump to those line numbers in your thing. I'm gonna actually shut the door so it's quieter. Might get a little hot. This thing works. Let me turn up the air. You can turn up the air in the back if you want also. Okay, so show of hands, who has actually, I'm just going to go into my command line as well, so in my home directory. Who has run Python before and gotten the interactive prompt in Python? Okay, kind of. Okay, so on all your computers, you should be able to like type Python, hopefully, and something works. If you're on Windows, you have to actually install it separately. No one is on Windows, right? Someone is on Windows? Okay, do you have Python installed on Windows? Okay, so you can run Python and it shows the prompt. Okay, good. If not, you could follow along on here. So, a really basic introduction. Again, this class is not going to introduce Python in particular, but a very basic introduction is that it is, it's an interpreter language. This thing is still going. It's basic. Oh, someone's trying to get in. Trying to get in. Or not. Someone's trying to get in. Hi. Are you registered for this course or are you auditing?
Actually,
You're auditing. That's fine. Yeah, it's fine. Just hang out in the back. So let's see. Okay, so what Python is, it's an interpreter language. Let me minimize this recording thingy so it doesn't get in your way. How does this? How do we minimize it? Good. Screen recording. Okay, so it's an interpreter language where you can write whatever you want. So, the simple thing is print, quote, hello world, and then it prints hello world to the console. You could use it as a calculator. You can say 1 plus 2, press enter, and then it prints 3. You can say x equals 1, And then when you say x, it gives you 1, or print x. And then y equals 2, y, and then z equals x plus y, and then z is 3, print z is 3. So it's, you can learn the language syntax by your own. It's fairly straightforward as far as the language goes. Has all the usual things you expect: variables, integer, strings, if statements, for loops, all the kind of functions, objects, all the things that you learn in, say, like Java or C. But it's, it's this really nice, simple syntax. So besides running it from the interactive prompt, one of the nice things about kind of an interpreted or dynamic language is that you can run it in a prompt, but you can also write a text file and run it. So I'm going to get out of here. I'm going to just edit a text file. I'm going to call it test. Actually, I'm going to remove it. Let's call it test.py. You guys all follow along and just write something. Let's say x equals 1, y equals 2, z equals x plus y, print z. Okay. So we're just taking a minute to write this file. We'll actually just use this as an example. So write this exact file for a bit. The font a little bigger. Font. Window. That's totally not the font. Here we go. Also see me mess with fonts. Let's try 18. Okay. You all see them in the back, right? Okay. Okay, so does everyone have this written? Wait one more second, and then for those of you with it written, we can just go to the command line and actually run it. So run python space test.py. Make sure it prints 3 to the screen. So we're gonna have I want to keep this up. Here, let me just move this so people can see it from the corner. Oh, it just happened. Space is at a premium. I'm going to open another one. I'm just going to move this over so you all can see it. Okay, so in the same directory, if you do an ls, you should see the test.py. So when you type python space test.py, loan of the whole, it prints 3. So has everyone gotten that to print out? Okay, so I'm just going to move on. I'm going to assume you have this printed out. If you have problems with running Python, especially on Windows, installing is a pain. So if you have problems installing it, let me know later. We'll get this fixed out. But sorry, I did not say that the prerequisite this time is you actually have to run it. So I shouldn't expect you to actually run it, because most of it is just reading the code and running control. Okay, so this is all good, magic. So the rest of this class, we're going to go over what the heck just happened there. Doesn't seem like a lot happened, but a lot actually happened. So conceptually, what we have here is we have a Python program. Let me actually, Windows. Windows is trying to be too helpful. Does this work? You're also going to watch half this class, watch me struggle with Windows, because I don't use Windows normally. Okay, let's do this. So we have a Python source code file. Wow, this thing is totally gone. So we have a file here. Is this really going? Okay, we have a file that has a bunch of code in it. It's called test.py, and we run Python with test.py as the argument, and then it does the thing in the file and it prints this 3 out to the console. So that is what we're working with. So I'm going to go back to the drawing app to dissect what is going on. So you can take notes in your own freehand, or you just watch along. So conceptually, what just went on in this craziness was we have this is a review from last time, for those who were last time. So we have wow, what the heck is going on with the pen? I apologize. That's so weird. This pen is not energized. All right, I'm gonna have to go no pen then. Okay, well, we'll go no pen. Apologies, this equipment today is failing. But so what we have is, no, this pen totally doesn't work. Conceptually what we have is we have a source code file here, and we are running it with a with the Python interpreter. So what actually ends up happening is that, remember, like I talked about last time, there's a compilation step. This file actually gets compiled into a piece of runnable code, and then the Python interpreter runs that code. So the Python interpreter doesn't actually, you might think conceptually, to learn, you might think it actually just runs one line at a time like this. Y equals 2, it has some variable 2 that it, some value to it assigns to variable y, and then this runs the second line, and then runs the third line. So conceptually that's what happens when you're learning, but under the hood there's a lot more going on, because it doesn't actually just run the source code. So what actually happens is we can actually just go through this step by step. I'm going to clear it again. I'm just going to type Python, just enter interpreter. So if you all want to watch along, let me make this smaller and make this bigger. So I'm in the interpreter, and what I'm going to do is I'm going to type this line in. So C equals, you can follow along, compile, parentheses, quote, test.py, quote, test.py again, doesn't really matter, and this is called exec. So this is the line I want you all to write. Let me go over what this does in a sec. So it's a function call to compile. Wow, pen is totally busted. Interacts badly with this stuff. Okay, so if you hit enter, it should do something. Okay, so no output is good. So does anyone have an error when they hit enter? Nothing? Okay, so press C, or just type C and press enter. It should say code object. Does everyone see that? Okay, good. Feel free to raise your hand if you don't see that, because, again, this is not super essential, because if you don't see it, you can just follow along with me, but it's helpful if you can poke around by yourself. So what this line just did was actually, let's see what it does. Say help. So in the Python interactive prompt, you can just say help for any function. So help compile. So help is a function, and you just call it with the name of another function or whatever in the Python interpreter. I'll give you a help screen. So press enter. Ah, sorry, the font is terrible. Your font's probably better than mine. Ah, look at that, it's good. So compile is a function that takes a source code file, just a file name. The second file name looks confusing because, like, why do we give the file name twice? This is actually what I think you'll call it. Yeah, look, file name will be used for runtime error messages. So it's just whatever you want to call it. If you want a cleaner name, because the real source is like the path or something. It could be really long. You can make the file name cleaner, whatever. It's just you put the same thing in, and then mode is the really important one. So the mode must be exec blah, blah, blah. So we did exec exec to compile a module. That's what we did. So a module is a conceptually just one .py file. Every Python py file is a module. So we're compiling the whole file at once. And feel free to stop me and raise your hand if you have questions about any of this. So this is all that we did. And you'll normally not do this by hand because the Python interpreter does this all under the hood, but I'm just showing you kind of peeling apart. So C equals compile this thingy, took the text file. I can point, right? Yeah, okay. I can still point, yay. Okay, I can point. So it took the text file. This is just the whatever, and exec is the mode. And it compiles it into a code object. So C, whatever you type in the Python interpreter, it'll show you what it is. So you don't actually have to say print. So C, this says it's a code object. So it's like, what is this code object? This is actually the compiled code. So we took a bunch of source code, which is written in English, sort of, right? Or whatever pseudo-English this thing is. That's test.py. We took that, and then we made it into the C mysterious thingy. So to look inside any object, you all can take notes on this because this will be useful for your projects or for even looking at what's going on, but this is just general useful Python-ness. So if you say dir C, dir is, it's like an old DOS command. It shows you everything that's inside of an object. So there's a bunch of junky things, but there's a few that are sort of useful. So the most useful, again, this is all documented somewhere. So the most useful is co_code. So if I now say C, actually let's see what happens if I do help C. Ah, look, it actually shows you the code object. So I did help C. So help, sorry. Let me make this font so we can see it. Wow. Bear with my terrible Windows-ness. What the heck just happened? As you can tell, I do not ever use Windows. That's the only tablet I have. So help C will show you that, it knows that C is a kind of code object, and it shows you the documentation for a code object. Descriptions for data. Actually, this is not useful at all, sorry. It just shows you what these fields are, but you could get this with dir also. So usually if people actually bother to document their code, the documentation will show up here, but they obviously didn't bother to document it. So the most useful thing, so dirc again, so it has a bunch of these things that are mysterious. Co code is the one you want to look at, so c.co_code. So type that, c.co_code. And this is an access of a field within the object. C is an object. There is a thing called co_code inside of C, and then you use the dot to get it. So this is like in Java or Python or whatever other language. Now press enter. What do you see? So you probably see something like this. Is that the exact same string, or is it a little different on yours? Okay, same. Okay, good. Having you compare the strings is terrible. This is called a byte string. So if we say type c.co code, actually it's a string, but it's a string. But this encoding is some like weird, crazy things. It's like /XOO. It's like not a string you would normally see. But what actually this says is that, you know, I think XOO is just hex for 0. So this is actually literally the byte 000000000 and 011, because these don't actually have like a letter associated with an ASCII. So this one, like S, is probably some number.
And why would you have J if it's hexadecimal?
Because it can actually display it, right? So like J is displayable, but 0 is not displayable, right? Like hex 0 is not displayable. It's like some null character. Maybe, but let me actually show you something else to resolve this conflict. Again, none of this is like absolutely necessary for you to know, but I'm just diving into the thing one step at a time. In c.co code. Let me see if this works first of all before you type it. That's okay. All right, let's try that. So do byte for byte in co.co code. Who has seen a Python list comprehension before? This sort of structure. Okay, a few of you, but most of you have not seen this syntax. That's okay. I mean, Python is not a prerequisite for this course. So what this weird thingy does is that in Python, a bracket, this means a list conceptually in Python. So like in Python, you can have a list of 1, 2, 3, 4, 5, or whatever. It's just a list of numbers. This syntax basically says we want to create a list by actually iterating over something. So c.co code is a string. It's just a string. Actually, I'm going to type it out again. So don't worry. You don't have to like type out everything here. I'm just going to just repeat it. So any string or anything has a length. So len gives you a length. So if I do length of this, it's actually 11 long. There's 11 things in the string. And if we painstakingly count, we can see there's 1. This escape code is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or something. What this byte for byte thing does is it actually just creates a list, one element for everything in the CO code. So it actually breaks this thing out into a list. And notice how this list has 11 things. 1, 2, 3, 4, 5. So does that answer your question about the J? Because the J is actually a byte, and this 000 thing is actually a byte. Okay. It's just that that's how Python displays it, because it can't display 0 or 1, right? This is literally 00001 in bytes. But J it can display because it's ASCII. It's not terribly informative. So this is not terribly informative because you're like, what the heck is all this? So another thing you can do is you can press up. I'm trying to see if I remember this. ORD maybe. Again, don't need to know any of this for reals. These are just arbitrary things. Oh, good. Perfect. Okay. So what ORD does is this has like absolutely nothing to do with the Python interpreter, but I just want to see the point of this first lesson is I want to show you there's absolutely nothing crazy hidden behind the scenes. Like absolutely nothing is hidden from you. So what ORD is where's my pen? ORD is a function that takes a byte, I guess, and it prints out the number, like the integer number associated with the byte, just for human readability. So this weird string here, this like x00 craziness, it's actually literally 0 in the computer. So when I say ORD of that, it will print out 0. So it actually, say it says 101. So 101 is the ASCII byte value for E, I'm betting. And then 0 is this 0. 0 is this 0. J is 106. 0x1 is 1. 100. Does that make sense? So again, this is not like super necessary, but if you look at the ASCII table,
Yeah.
this makes sense, right? So I have the ASCII table memorized. That's good. Let's zoom in. So 80, what the heck? 10, wait, what are we? 111? 101. Yeah, 101, right? 101 in ASCII is the letter E, right? And then whatever 106 is the letter J, because this thing 106 here is the letter J. It's just a way of printing it. But really behind the scenes, I guess the lesson I'm trying to get at here is that these are all just numbers somewhere, right? And you know, this weird convoluted Python string, which you don't even memorize, is how you get all those numbers out. So now you should be able to see why. So this code is called bytecode. And now the light bulb's like, oh, it makes sense, because it's a code of bytes. Right? That's all it is. Everything is 1 byte. And you have a bunch of code, and there's a bunch of bytes, and that's it. So this code that we have to not forget where we came from. We came from this, right? We came from this nice looking piece of Python source code written in a language called Python that was nice and beautiful, and everyone can read it. And then we went into this thing. It turned into a list of bytes necessarily. Now, it's not really a list, it's actually a string, right? It's just a bunch of bytes plopped together in memory somewhere. It's a string like this, so it's really compact. Everything is 1 single byte. We just did some magic fancy printing in Python to get all these numbers out. 101, 00, 106, 01, 183. So let me copy this so we could have it for reference. Actually, instead of copying, I'm just going to leave the terminal open. I do some magic. I will try to get better at Windows, I promise. Okay, I'm going to do it again. No magic. Okay, see those numbers up there. Do you see the exact same numbers? Okay, it should be exactly the same. For the exact same version of Python, it should be the same because the code should all be exactly the same. Okay, so now the question is, what the heck does this mean? So does anyone have a guess at what this means? What does that string of things mean?
It's the opcode and the operands.
Okay, it's the opcode and the operands.
That's the instruction set for the virtual CPU that is in the runtime of the Python environment, I guess.
Right. So we had a lot of words. There's an instruction set. There's a virtual machine. There's a runtime. Good. These are all good words. So we'll elaborate on all these. So will you be able to look at that code and tell me what it does? I hope you're not, because otherwise you shouldn't be in this class. You're actually a Python interpreter.
X to 1 and Y is 2.
Good question. All right. X equals 1. You know, it's like the matrix, right? You're actually just reading this code. Y is 2 and Z is X plus Y.
We need to have some sort of table to decode this.
Right. So we need some kind of table to decode it. Okay, good. That's a great answer. Yeah, so that is actually this, you know. Somewhere in here, somewhere in here, we have this. So let's actually look at opcode.h. Actually, let's not look at that yet. That'll ruin the surprise or something. So now let's open up another terminal, completely new terminal, in your same home directory. How do I open a new terminal? Are you kidding me? Let me open up a new terminal. Oh my gosh. You have to work with somebody has to work with this great window manager. Can I open new? Are you new terminal? New. Yes! Okay. This is getting ridiculous. Okay, let's see everything on the screen. Because I want to just make sure everything is on the screen. That's why I'm going through all these contortions here. Okay, so obviously reading the bytecode like this seems silly because we don't know what it is. Fortunately, Python has a really useful module for what's called disassembling the bytecode. So remember test.py is here. So what we're going to do is we're going to run, if we run test.py, run 3, okay? No questions. Now what we're going to do is say Python space -m space dis space test.py. So type that out and then press enter. Okay, so you should see it like this, something like this on your screen. Does everybody see this? Is there an error? Hope there's no errors. And we see, I think, exactly what we want to see here. Okay, so what this is, it's called a disassembler. It actually just took this, compiled it, and then printed it out in a pretty way. Because inside the library, it knows what opcode is what, it knows what 101 is, and it knows what 0 is, and knows what 0 is, and knows what 16 is. So I'm betting you 101 is this load constant thing. Actually, I don't want to bet because it might be out of order. So conceptually, this is the bytecode. And notice the general format is that there is a name. These bytecodes each have names for what kind it is. And then there's a line number. This 1, 2, 3, 4 is actually a line number. So line 1 is this one. Line 2 is these commands, these bytecode. Line 3 is here, and line 4 is here. So the first thing to notice is that every line can have more than one bytecode. Right, that makes sense? Now line 4 actually has 5 bytecodes. Line 3 has 4, and line 1 and 2 each have 2 bytecodes. So there's not a fixed number per line. So one line of source code can go to multiple bytecodes. And this line number is just useful for debugging because when you're stepping through it, it knows what line it's on. The second figure here is actually the byte offset of the thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hold on. I think we missed 1, 2, 3, 4, 5, 6, 7, 8. It might have added some stuff, maybe, because it wraps around. But okay. Is there extra?
Like, I have a question.
Yes, question.
What is the, you said there's 11.
There's 11 bytes here,
11
yeah.
bytes there, but so one byte could be multiple instructions, actually?
Yeah.
The number is not really 11 instructions here, right?
That's
so
right.
How does that work? Do
Yeah.
they have any correlations?
Yeah, so I think it's actually more compact than that. So I think I need to go into that. We need to go in the H file. Right, but basically the question is there's 11 things here, but there's more than 11 things, ish things here. Some things have arguments. You don't actually need, you don't actually need to do the byte level thing, but we'll go into this as we look at the H file. I think that will be uncovered. But fortunately, even though we're going in the interpreter, it looks like it's all convoluted, the interpreter has macros and functions to wrap around all of that. So you don't need to actually do all the byte switching yourself. So pretend like this actually maps semi-correctly. Let's actually do this now since you brought this question. So let's go to opcode.h. So just the file opcode.h. So don't worry about the interpreter. This one, opcode.h. Okay, so I'm going to make the font big. This is a header file that basically has a bunch of pound defines that define what these opcodes are in numbers. So let's actually find the one we want, which is load const, LOADCONST. Which stands for load constant, as you can imagine. So this one right here, 100. Okay. So load const is the bytecode number 100, and it is a bytecode that actually takes an argument in. So some bytecode take no arguments, some bytecodes take arguments. So if you actually notice here, this 99 or this 90 thing, it says have argument. It's just a placeholder. So every bytecode above this is in the opcode. Every bytecode above this takes an argument or takes some kind of argument. Everyone below this takes no argument. And I'll go over what this means in a second. So all these above take no argument, and all these above 90 take some argument. So I don't want to spend a ton of time trying to map it because I'm not exactly sure in my head, and you don't really need. So load const is 100. And so this class will not be about, just as a warning, this will not be about like matching up numbers. So don't, I'm just going a little too little, don't worry about this too much. So this is, where is the other one? Yeah, so this is 101, and I'm betting that the extra 1 is the load constant of 1 here, even though we need to figure out how. So I think as an optimization, so it actually loads the constant 1, and then 100 is the opcode name, and then it just adds an extra 1 to it because it can. But that's not obviously safe because you can have a giant constant. So let's not worry about this too much. What we're going to do is we're going to just, gloss over just basically, this code is mapping into here somehow. The bytecode format is compressed, as you can tell, right? It's actually compressed.
You also mentioned that it could be out of order.
Right. Actually, I don't think it's actually out of order, so I shouldn't say that. The bytecode's pretty simple. It's not out of order.
Okay.
But it is compressed. The debugging from it, it is really compressed because it actually has the line numbers and stuff too, and all the line number info. So it is actually really weird and compressed. So you shouldn't actually be able to read this. But the disassembler knows how to read it, and there's some rules. So let's actually from now on just concentrate on the disassembler output. Okay, so reading this output, what we can see is we're going to do a load constant of 1. 1 is a constant. And then store name stores into x, which is a name or a value. So if you actually look at line 1 here, it kind of makes sense, right? X equals 1. Conceptually in the machine, what it's doing is it's loading a constant 1, and then it's storing it into some piece of memory name with x. Does that make sense? And then 2, same thing. Load constant 2, and then store 1. Store y. All right, so y equals 2. Yeah, these are all super encoded because like 106 is. Yeah, so maybe I'm just gonna just humor me for a second. Oh, it's constant. Maybe the yeah, I'm not even going to try to decode this because there's all sorts of guesses what it would be. But just trust this output. So this second line is load constant of a 2 and then stored in y. Okay, so what is
what does the 1 mean?
These? Yeah, these are this is actually the offset into, actually this is good we did this. This is actually, we're actually not storing x, right? Because x is just a mnemonic. It's actually, we're storing into the 0th local variable.
Oh, okay.
And then we're storing into the 1th local variable. Same thing, there's a constant list, you could say.
Oh, I see.
And we'll actually see this in interpreter. There's a 0th constant and a first constant. So actually we go back to here, maybe miraculously this will work. There's c.co const. Okay, that didn't work. c.co
variable names.
Names. No, this is not.
They're var names.
Sorry. C.co var name. No, so it does hide something when it The other annoying thing about this is that the bytecode does optimize some stuff away. There's a way to turn this off, but you have to actually recompile the whole interpreter, which is annoying. So it kind of hides some stuff from you. But if you're really, really curious about this, and this is, again, I'm just throwing out ideas here for projects. So, this sort of thing is actually really appropriate for a project idea. So for projects, again, like I mentioned in the first class, you could either do something in C and modify the C Python interpreter, which is like pretty hard and scary, which is awesome to do. But most likely you could be just doing a project in Python itself, analyzing code. And that, there's all sorts of tools available. So to actually answer your question, so some of you had a question of how does this actually generate this nice output, right? It must read this stupid code here. It must read this silly thing here, this series of numbers, and like print something sensible. And the solution is that actually it's just a standard library file. So all it is I'm just going to go. So what Python mdis is this actually runs a module called dis.py, and it finds it in the standard library and runs it. So I'm going to show you where it is actually. So if you're curious where it is, it's actually in Python lib, capital Lib. So if I do an ls in this directory, python278/lib, you can actually look in the text editor. There's a bunch of py files. These are all the Python files in the standard library in Python. So Python comes not only with the language, it also comes with a giant library of functionality. This is why people really like Python, because you can import whatever, OS, mail, blah, blah, gzip, hashlib, all this stuff. Majority of it are actually written, the standard libraries in Python itself, which is nice because you can study the code. Some of the standard libraries in C, because for performance reasons, but dis is actually in the standard library. So I can actually look at dis.py. Actually, let me look at it in Sublime, since we want to stick with Sublime. Are you kidding me? Dis.py. So dis.py is disassembler for Python bytecode. This is just a Python file. So this is the answer to all your questions. The answer to all your woes is in here. It's just a Python file. Like it goes through this code object and does some crazy things and prints out crazy things. That's all it does. So everything is in here. Like it has some like crazy conditions and compression and stuff. But really all it is the main function. So in Python, the main is written like this. It's kind of awkward. So what Python-m, I know I'm going to a lot of Python that's not part of the core, but this will be helpful later on. What -m does is that it loads the module, dis.py, you don't have to put py, and it runs the main function. And the main function here runs _test when there's no arguments, I guess. And _test is, again, all this you can trace for yourself. _test, if you look at it, it's, wow, what does it do? It just does that. It's exactly what we just did. It just calls compile like we did. There's no magic here. So I did this convoluted thing, because that's all it does. It just compiles it into a code object, and then it calls this magic dis function on code. And dis is the magic. That's all the solutions to the Earth questions are in dis, and it is some crazy thing. But as far as we know, it prints out this output. As another aside, remember, if you're curious about analyzing bytecode, this is a great set of ideas for projects, because bytecode is fun to analyze. If you want to analyze or play with bytecode, I would not recommend using dis.py, because if you notice, all dis.py does is print it out for you. It looks ugly, you have to parse it, it's just a bunch of text. I would recommend this library called byteplay. It's called, again, remind me later, I can show you later. This is not necessary right now, but if you Google for byte play, byteplay, it's codegoogle.com, byteplay, Python disassembler. It's just a single py file. All it is just a nicer version of the disassembler. So what byteplay lets you do is it actually lets you disassemble into a nice structured object. So you can actually manipulate the bytecode and query it and move it around. It's quite impressive. And this only works on Python 2. Remember, there are 2 versions of Python 2 and 3. Another reason why we study Python 2 in this class is that there's better tools for Python 2 than Python 2. So byteplay is one of them. But byteplay is pretty robust. Like if you look at this, according to them, that's pretty robust. I haven't tried this, but byteplay is pretty reliable, according to them. Python's complete test suite continues to pass after you use byteplay to disassemble all the code in the standard library and assemble it again. That's pretty cool. So basically saying you use byteplay, run it, disassemble it into byteplay objects, and then reassemble it into the code and run it, and all the tests still pass. So it's like a pretty good test. It means that it didn't break anything. So I would trust it. 2627, yeah, 27, good enough. So you can use this for playing with your bytecode. Again, don't need to for right now. Okay, so we want to actually go through this code and see what happens conceptually. So conceptually what happens is, let's see. I really wish the pen works. Hold on, I'm gonna go try the pen one more time, because this is totally in need of drawing. That's so strange the pen doesn't work. Okay, I might just go do finger painting. All right, let's see how well this works. Accept this thing is like, the touch screen is weird. Okay. Close enough. What is this? No windows?
Only reason not to buy Windows for that.
Yeah. Well, sorry for those of you who have Windows here. Okay, we're gonna do finger painting. Now let's let me pull up the code here. Yeah. I'm telling you, you're getting your money's worth in this class. Okay. All set? Source file on the right, bytecode on the left. Okay, we're going to actually execute this code as though we were the interpreter. Okay, so we're going to execute this code. So all the interpreter does is that it just goes straight through from the first line all the way down, one line at a time, and executes. So first line is load constant 1 somewhere. It just loads it. So now where is it loading it? It's loading it in what's called a value stack. There's actually a stack. Some of you might be familiar with like a stack when you're calling functions, right? Like when you're calling functions, foo calls bar, there's a stack of functions. In the Python virtual machine, there's an additional stack called a value stack. This is gonna. Do you all like the stack to go up or down? Which is better? I don't really care. Up, down? All right, let's do down, because down is what people usually do. Counter do. Okay, where the stack goes down. Good enough. So there's this thing called a value stack. That is here. So value. Wow, this is terrible. Sorry. There's a value stack that is just a bunch of objects. There's just a bunch of stuff. So when you say load const, that pushes an object onto the stack. And when you execute this code, it actually pushes an object called 1 onto the stack. All good? So there's one thing on the stack after this. This is not a function stack. There's no functions here, by the way. There's just one piece of code, no functions. Now we're going to go line 2, store name. Store name takes whatever's on the top of the stack, pops it off the stack, and puts it into a spot in memory associated with the name. So when you execute store name, this thing actually gets popped off the stack. Let's try this. This gets popped off the stack. Nothing on the stack. And where does this go? This goes somewhere else. Like that. In memory. Does that make sense? So after store name x is 1, x points to 1. Nothing's on the stack because store just popped it off the stack. So the Python virtual machine is what's called a stack machine, as you can see. There's a stack that you're operating on with values. That is a very fundamental key concept. Okay, let's go to line, let's go to the next instruction. Load const, same thing. We're gonna load 2 now. So load const pushes 2 onto the value stack. Then store name does the same thing. It pops it off, and then it puts it here. So y, sure you're all amused by these drawings, and then pops that off. Make sense? Okay. So what happens in the next step? Load name here. Oh gosh. Okay. So somebody tell me what happens in this step now, given what we've seen.
Push something and push one object named x into the name stack, the variable stack.
Okay. So we have one hypothesis that it pushes the x thing onto some stack of something. Any other hypotheses?
We should do the stack with the add function.
Sorry?
We should do the stack with the add function.
Okay, push the stack for the add function. So maybe the add function has some stack because we might want to. We're gonna do an add later. That's a good idea. But the thing is, when the interpreter is really dumb, right? It doesn't know there's an add function coming up. It's a good thought. So if an interpreter is smarter, it would look ahead, but it doesn't. It's pretty stupid. It doesn't actually know. All it knows is all it sees right now is load name x. So other ideas. I mean, these are all somewhat on the mark. So other ideas. What should go on the value stack now? Be more precise. So load pushes something on the stack. That's right.
Object 1.
The object 1. Okay. Other ideas for what could go on the stack? So your other suggestion was the name x, right?
Yeah.
Okay. So we're either doing, either this x thing is going on the stack, or this one thing is going to the stack, right?
Should be the x.
Should be the x, you think?
Because there's a 0 in front of the x.
Right. So it's actually the 1 because the value, because it's a value stack, right? So it's actually, no, this is, well, that's why I didn't want you to pay attention to these zeros and ones because these are just internal. So pay no attention to these 0, 1. That's just internal bookkeeping. So the real thing is these x and y because if you pay attention to this, it will confuse you. Really, this instruction is load name x. So what this does is that it will load whatever x contains, right? X, it will look up whatever x is, grab its value, and then push it onto the stack. Now here's a kind of tricky question. What happens to this thing, this one right here that x is pointing to, this object? Because before when we popped it, we x'd it. Do we kill this now? Do we go like this? Does this die? So you say no.
I think it's still there.
It's still there. Good, good. It's still there. I can't undo, sorry. It's still there. The reason why is, right, just loading it doesn't mean we're going to delete it from memory, right? That would be kind of crazy. Because what if someone else needs this x, right? Yeah, we don't actually destroy it. So this brings another point now that actually I can't draw it too well here. We'll see this in the interpreter a bit. Don't worry if you don't get it the first time. What really this is that there's actually not a, you notice how I seem to have made a copy of the 1, right? There's actually not a copy. There's only one object called 1 here, but there's just 2 pointers to it. There's actually 2 references. So this thing is actually one thing, but I'm just referring to it in 2 places. The value stack refers to it, and x refers to it. So you can imagine if we were in the hyper 4th dimension, there's only one thing. What this concept is, it's called reference counting. Gosh, this is terrible. It's called reference counting. And this is how the Python interpreter does what's called garbage collection. So this one object actually has a reference count of 2 now. 2 things are pointing to it. And when you actually pop it off the stack, the interpreter code actually has to decrement the reference to say that there's only one thing pointing to it. And then let's say somebody, in a hypothetical future, can we do this with the other pen? Let me see. This is an alternate future. Don't worry about this world. Imagine we killed this one, and now only x points to it, and then we killed this x reference also. Then there's a 1 object floating somewhere, like just junk, it's garbage. Then what Python does is it actually deallocates that memory so it doesn't, that you can reuse it for something else. And it does this by keeping track of the references, but we'll get to this in a later lesson. So getting back to the heart of the matter here, okay, we push this on. Now it's crazy messy. All right, next step. So what happens to the next step? What happens to this load name y? What gets pushed on the stack?
Object 2.
2, right? Object 2, good. And remember the stack grows down because you all wanted to grow down. So this is stack is going down. Just push it on the stack. Okay. So what is binary add? What do you think that does?
It adds the binary numbers for the representations like the 1 and 2.
Uh-huh. So where does it find what to add?
It goes back to the stack.
The stack, exactly. Because there's nowhere else. So what binary add does, you're absolutely right, is that it goes to the value stack. It finds, how many things does it find on stack? 2. This is binary. Good. So it finds the top 2 things on the stack. It doesn't care what it is. Finds the top 2 things and adds them. So what do you think happens to the stack after this? I haven't actually told you this. So what does the stack look like after the binary add executes?
It's going to be a result of the add.
Okay. So what should be on the stack?
Object 3.
Object 3. Where should I put the 3? Here?
Eliminate 1 and 2 first and push 3.
Okay. Eliminate 1 or 2 first. You all agree? So, right. So we don't want to leave this here because then 1 and 2 are junk. So you're absolutely right. So what this does is what a binary add does. This is part of the specification of the opcode, the instruction. All binary operations take the top 2 things on the stack, pops them. Oh, that was terrible. Oh, you got the point. It pops them and then it puts the 3 back on. So, value, stack, never press the erase. So it pops the 1 and 2 and it puts the 3 back on. So remember, x still goes to 1, y still goes to 2. These have not changed. pops and puts 3 on. So we did this, 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 this. And then what does this last store name thing do?
Pop it off the value stack.
That's right. Pop it off stack and then put it on Z. So Z is 3. Never press the trash can. So now value stack is empty. We have all this stuff wonderfully in memory. X goes to 1, Y goes to 2, Z equals 3. It seems like a wonderfully trivial and tedious example, but you know, if I actually showed you real code, it would be impossible to go through, right? So notice how just one silly line of code, it's 3 lines of code. We just executed 3 lines of code in the interpreter. Yeah, that's a lot of work. Fortunately, the computer does a lot faster than we do. So we did 3 lines of code. So notice how here we have, it looks like what we want, right? X is 1, Y is 2, Z equals 3. You can print it all out. It's all good. There's nothing on the stack. Now the last line here has a bunch of stuff, so we'll go through it really fast. Load name Z. This loads the Z thing on the stack, so it looks up 3, puts in the stack. Print item. So print in Python is actually a primitive operation, at least in Python 2. It's a primitive operation, so it actually has an opcode for print. So what print does is that it takes the top thing off the stack, it pops it, ooh, it's gone, and then it prints it to the console. So that print opcode just smashes it to the console. That's what lets you print. Print normally doesn't give you a new line, so it prints a new line as well. If you say print in Python without a comma in the end, it just prints your thing and a new line. So it's actually 2 separate opcodes, the item and the new line. And the reason why is because you may want to print a bunch of items without a new line. So again, opcode is a little bit more verbose. All these opcodes are detailed in documentation I'll show you, so you don't need to like remember 0, 1, whatever. And there's like no tests in this class. I'm not gonna ever test you and say, what does opcode 25 do, whatever. See, it's all, it can be referenced, all right? This is not an undergrad class, right? It's all can be referenced. Load const. Okay, so the final step here seems silly. Load const none return value. So load const none is a special constant. It's a special constant in Python. It just represents nothing. So what this last line does, just for completeness, is that it loads an object called none on here, and return value actually tells it to pop the thing off the stack and return it to its caller. Because everything in Python is conceptually a function. So we notice how we didn't have a return statement here. We can't have a return statement because it's a module. There's actually no return statement, but everything just returns none by default. So this will come in handy when you're actually calling functions. So don't worry about this, just some extra code right now. But conceptually, the really core part I want you to see is basically these lines. Does that make sense? So that's exactly the bytecode for this. Okay, so I'm going to spend the next 10 minutes or so on the interpreter. I know this is going to go a little bit fast, but we're going to actually have you do it as part of the code annotation assignment for Friday. We're going to have to do more for the assignment. So going back to this, let's look at the opcodes again. So let's actually go to the text editor. So now hopefully this is all seared into your memory. And let's kill this.py. Remember opcode.h? These are just a bunch of numbers. Like they actually don't have no meaning, right? It's just a bunch of numbers, so it knows. I just wanted to show you that these are actual opcodes. That pound define is a macro in C, so all it just does is it expands this number. So whenever you see binary whatever in the source code, it's just the number 64, and it's just, again, just no magic. Okay, the real thing I want you to look at in the next 10 minutes is ceval.c. This is a giant file. We're not going to study all of it. Look at for a line like 690 or something. So jump to like line 690 in your favorite text editor. You're able to jump down. Or you could look for a function called pyeval. To figure out underscore. Let me try to look up the function name. Underscore eval frame x. I know it's a terrible name. Okay, it's line 693. I hope it's the same line for yours because I checked out the same version. Okay, it's called pyeval underscore eval frame x. 693. You can write a comment on it. You want my suggestion if you want to comment in the code is for right now, like not for your assignment. For right now is just a comment on the side because otherwise your line numbers get screwed up and then they don't match mine. You could comment separate lines if you want, but just remember the line numbers. This is the main interpreter. This is like where everything happens. Now this function Can we totally fold this? No, I think, so Sublime Text does folding of functions, but this is going to trip it up because there's a bunch of these if defs in C. Let's see where this function ends, first of all. So this function starts at 693. Let's see where it ends. It's really long. It's really long. It's still got. Can you find the end?
3021.
3021. It's the magic number. Yeah, you're also getting a great taste of, I never used Sublime before, I just used Vim. But Vim you can't scroll with the thing or draw it as you. 3021, perfect. So that is a 2500-ish line function. So first of all, never write a function that long in your own code. But so it ends on 3021 and it goes from 693. Okay, so a lot of this class will be actually in this function. So we're actually obviously not going to study all 2500 lines today. Today we're just going to go over very, very, very high level details. And as part of your assignment, we're actually going to have you annotate in this code. The assignment will most likely be, I'm going to give you a piece of Python code, like what we've seen, and we'll have you trace the execution through this interpreter loop and talk about some of the issues that it faces. So we're actually going to do a slightly more complicated example for the assignment. So this function, first of all, what does this function take as an argument? It takes a pi frame object, a pointer to a pi frame object, okay, and then some flag thing. Things like flags or throws are like exceptions. Don't worry about exceptions right now because a lot of the code is actually handling exceptions, so don't worry about it. And it returns a pi object star. So we'll study it in a future class. A pi object is just an object in Python. Everything in Python is an object, and it's called a pi object. So pi object star means that it's a pointer to it. So this means that this function takes a frame, which I'll tell you about in a sec, and does something and returns you an object. So you can imagine using this to execute a function. If you execute a function, then after you finish executing, you better return an object out to whoever called you. When we execute this module, remember we had this return value in the end, it just returned none, but it has to have some way of getting the heck out of there, right? You need to return something. Could be none. A frame is just like a frame in the stack. So right now, you imagine the frame we're executing is conceptually just this code right here. It's just a straight piece of code. Nothing fancy with function calls. Today we're not doing any function call. No function calls. So okay, so what does it do in the next 10 minutes or so? First of all, a good way to look at this code for you to take notes on is to like see what you can ignore right now. A lot of these if-def things, these are for conditional compilation. You can ignore a lot of these. A lot of these are for debugging and such. So the main things here that it's declared are these variables. It's really nice. The code is pretty clean. It declares it up top. Notice this stack pointer thingy next free slot and value stack. This is the value stack. So I'm happy to go over this in office hours. And also, by the way, my office hours are like right after this class. So if you have questions on like C or anything, happy to go over it. Because again, I'm assuming you're pretty familiar with C, but if you're not, happy to ask me offline. So usually in C, whenever you see a double star, that means it's a list of pointers or an array of pointers. So this stack pointer thingy it points to the, well, it says the next free slot in the stack. It represents the stack pointer for the value stack. Next instruction is what you expect, opcode, opargs, blah, blah. These are temporary objects, x, y, whatever. It's just as an optimization, so you can hold it fast. These are other temporary objects, return value. So this is the kind of heart of the local state here. All this crud down here are, hold on, let me see, TSC. So TSC stands for timestamp counter, I think. You can read all about this here. Timestamp counter. You don't need to know anything about this. What this does is basically it's a way of profiling and measuring how fast your code runs. So if-def TSC is like, if you really want to care how fast this runs, it makes really accurate measurements. You can ignore all of this. Like if-def TSC, this is all like crazy, like what the heck is that read timestamp? Just ignore all the timestamp stuff. We don't care. But I would suggest, again, for your assignment, don't just delete the code because then all your code is different than mine. You can just ignore it and make comments. These things are macros. We're going to actually have you do the opcode prediction and figure this out as part of the assignment, so I won't go over this. But these macros So who here is familiar or not familiar with C macros that look like this? Okay. Other people? Okay. So a C macro, this, pound define. First of all, there's two kinds of C macros. I should go into a little bit faster. You can ask me afterwards, but the first kind of macro is pound define something something. And that literally just means when the C code gets compiled, whenever you see this, it just pastes in this. It just pastes that into the code. These macros are a little bit more complicated. It basically means that whenever, these things have parameters. Basically, if you see a macro called jump to and you say 5 or whatever, it will literally more or less paste in the code, except with X, it's like a 5 there. So macros are just shorthand, so you don't have to keep writing the same code and code again. To first order, what it is, it just avoids you copying and pasting a bunch of code. Like all this weird code is being written again and again, so they put it into macro. And they actually give it a name. So next op means next opcode, next argument, peak argument, and so forth. And this is all, like your question here, this all encapsulates all this weird bit stuff. Predict, okay, don't worry about dynamic prediction profile. So this should be off, dynamic execution profile. So the predict should be this one. This is the predict one. And again, it's an exercise for you to look at what this macro means. We'll actually use this as part of the assignment. So definitely look up C macros, because this is a non-trivial one. It's like, what is this pound whatever thing? It actually has a meaning. These things manipulate the stack, if you notice. For example, top gets the top thing on the stack. Second gets the second thing on the, this is the value stack. Third, fourth. Peak means look at the nth thing. Set top is what you expect. It sets the top thing, sets the second, sets the third. Empty means, is the stack actually empty? Push pop. So push pop is what we were doing before. It pushes something on the stack, pops something on the stack. LL trace is some other crazy whatever thing. Else push pop. Don't worry. Again, usually when you see these if defs is another macro saying if this weird thing is defined, do this. Usually they're false. So usually we're going to use the default version. So if you notice, push and pop are just macros for basic push and basic pop. So it does what you expect. Push something on the stack, pop something on the stack, whatever. Get local, blah, blah, blah. There's a lot of stuff. Okay. Finally, 200 lines later, we're actually going to start the code. We got 5 minutes. 200 lines later, start the code. If the function frame is null, return null. Okay. Good call. Smart. We're going to end there. Okay. So if someone is idiotic past you a null thing, don't freak out. As you'll see, a lot of C code needs this because if you don't do this, then you get a null pointer dereference or some memory error. You got to handle all the stupid stuff. Enter. These are all things you can ignore, like T-state tracing. Again, there's a lot of stuff I'm talking to, but I'm just telling you what is safe to ignore. Right? You don't have to understand every bit of the code because this is a real code base, right? This is not just something I made up. Real code bases have all sorts of details. This T-state is probably some profiling thing. Ignore, C profile. A lot of this is just for debugging profile. Okay, so this is actually something you need to pay attention to. CO is the code. So the code we want to execute, we're going to grab from the frame. Talk about frames next time. Names, constants. Grab everything out. And next instruction, stack pointer. Okay, forget the LO trace. Okay, finally. Okay, 964. Make a note of 964. This is an infinite loop. Why do you think they write it as a for and not as a while? Good question. Any thoughts? Anybody have thoughts on that? I just have a guess. I don't know. I think it might be more portable. So the big thing with C is that people have all sorts of crazy C compilers, and maybe for is more portable than while. I don't know. But I don't know why the heck they do this. But this is basically an empty for loop. This is basically the same as saying while true or while one. This loop will run infinitely until something kills it. Part of the exercise is to see what actually kills it. So this runs infinitely, and all it does is conceptually, we have 2 minutes left. All it does is it's just a giant for loop. All it does is that it goes through your bytecode 1 byte at a time. 1 opcode at a time. We have to find where actually it goes. Next opcode, instruction, blah, blah, blah. Opcode, next op, okay. 1080. Extract opcode and argument, 1080. Again, this should all be familiar. It's just a lot of crazy C code. It's exactly what we did manually. No surprises, except lots of weird code. It says grab the next opcode from my string, grab it out, whatever it is. Grab the argument, if has arg, next arg. So some opcodes have an argument, grab the argument out. It's probably some, what this is doing is conceptually, grab this thing. If it has an argument, decode it, grab it, whatever. Do something. Next time in the for loop, do this, do this, do this, do this, do this, do this. We run off the end, we explode, and we're done. So we grab the opcode into a local variable called opcode, and lo and behold, all this thing is a giant, giant switch statement. So another thing to bookmark is 1112 switch opcode. It's a giant switch statement. So a switch statement in C is just like a giant if-else statement. It just says, what is the opcode? If it's this, do this. If it's that, do that. It's super, super dumb. There are some optimizations with all the beware. Okay, I'm just going to fly through this. You don't have to know all of it. But look, if it's a load fast, do this stuff, right? If it's a load const, do this stuff. If it's a store fast, do this stuff. Pop out, do this stuff. Most of your 3,000 lines is exactly that, right? It's like super, super boring. There's one for every one of the 100 opcodes. So all this does is do that, do its thing, go back to the top of the loop, or maybe not. There's some optimizations we'll have you see. Do the next one, and until the very end, where is return? Return value. Okay, so return value is one of them. It pops the return value off the stack and goes to fast block end. So goto is I'm just going to show you how it gets out. So find, this is in return value. Break loop also goes to end. Fast block end, so it goes like this. There's some craziness here because you can exit some other ways. And then end the loop, main loop. Yeah, so this is the main loop here. So if y is not equal to y naught or whatever, like this should be the case when you return, it just break. So this magical break is what kicks you out of this loop, and then you clean up, and then you, there's a lot of cleaning up, and then you return the ret val, return out of here. So there is a way out. There's many ways out, but that's the return way. Part of your assignment will be to trace through all that. But before we go, let's search for, let's do the binary add, just for edification here. Okay. So it's more complicated than I thought. So conceptually, what it does, we'll have you annotate this. Remember binary add. Remember what you were saying. It pops the top two things off the stack. Pop. Well, actually, it's an optimization, but it conceptually pops the two. It has to check that they're both integers, and if it does, you actually just do an integer addition. If it's not an integer, you do other stuff. We do all sorts of other stuff, and then it pushes stuff on the stack. So every operation conceptually just does something. So let's do a load const, actually. Okay, so this is a little simpler. Good. So load const. Remember load const. I'll let you go one sec. So load const is this, right? Load a constant 1, and what that does is it just pushes it onto the stack. It doesn't store it anywhere. It goes here, right? Load const, all it does, push it on the stack. So look at the code. It's actually fairly straightforward. X equals get item const oparg. So there's an argument, which is which constant you want to load. Const is a pointer to the constant pool, the pool of constants. This actually gets it and puts into a temporary x, not to be confused with the x in our code, temporary. Incref increments the reference count. This is, remember how I told you, you need to actually tell me, I am actually grabbing a reference to this, and then pushes it on the stack, and then it does this go to it. We'll let you figure out what this is. So we'll go over this more next time, but I think I'm going to release the assignment tonight. But you should be able to get started on it tonight if you want to get started. But by next time, if you're okay waiting until next time, you'll have a more general sense of this. But I think just from this, you'll have a sense to get started. So this is the basic bytecode interpreter in a really, really big nutshell. And you can just look through all this code yourself. There's a lot of other code to look through, but that basic thing, don't worry about the profiling or a bunch of the if-defs. So the key thing with the assignment, I'll just give you a preview, is what is this fastnext opcode and what is this predict business? Fastnext opcode and predict. Because I'm telling you, the basic dumb thing is you go to the opcode, goes through all the way to the top of the loop, goes to the opcode all the way to the top of the loop, but the interpreter is a little bit smarter than that with some optimizations. And for the assignment, you will have you try to figure out what all this predicting and fast opcode thing is.